So in this tutorial, I'm going to show you different approaches to solve net force. Basically, it's different techniques of just breaking down force components and adding them. But you may find by looking at these that you like one method over the other. So let's start off and talk about a problem we did in class where we broke up our forces, into its components. So in this case, there are several different methods that you can use. I have three vectors pointing away from this object. And so I'm just going to go ahead and just write my list of forces here. So I have force 1 is going to be 600 newtons at 45 degrees northeast. And force 2 is going to be equal to 250 newtons west. Force 3 is going to be 500 newtons south. All right. So these are all the vectors that I have, force vectors, pulling on this object. So I can change this into multiple different approaches to solve this problem. And so what you use for these vectors is depending on which method makes sense to you. Now, I can convert these forces, the 600 newtons, 45 degrees northeast, I could just rewrite and say, hey, this force is actually 600 newtons, 45 degrees from the positive x-axis. And all of these are going to be taken from the positive x-axis. My force 2 is going to be 250 newtons at 180 degrees because that is what's west. And that's from the x-axis. And I could rewrite my force 3 as 500 newtons at 270 degrees instead of saying south. So this is one way I could lay this out as a trig type problem. So let's go and draw this. So on this graph, I could just pretend that this little box is at the origin. And that I have force 1 at 45 degrees. For some reason it doesn't like me drawing circles. And then I'm going to use purple to be my force 2. It's pulling to the west. And then force 3 will be green, which is 500 newtons south. Okay. So I could just look at this problem and say, okay, force 1, and break this down as its own triangle. So I can draw my force 1 triangle. I know the length of the hypotenuse is 600 newtons. And so there's going to be an x component for force 1. And there's going to be a y component to force 1. And so I could use these subnotations of force 1, F sub 1x and F sub 1y. And I know just using trig that my force 1x is going to equal to 600 newtons times the cosine of 45 degrees. I drew my little triangle here. And I can also see that force 1y is going to be 600 newtons sine of 45 degrees. And since it's in the first quadrant, I know that both my x and my y are going to be positive. I could also look at my graph and say, okay, now I have force 2. Force 2 is at 180 degrees. So I could either write this as force 2 sub x is going to be equal to the 250 newtons, which is the length of force 2, cosine of 180 degrees. And some of you may already be able to see that, oh wait, cosine of 180 degrees, that's just negative 250 newtons. And then force 2y, many of you can already see that that's going to be 0, but if not, you can just write this as 250 newtons times sine of 180. Now note, all these angles have to come from the positive x-axis in order to write them this way. And so this should automatically say, hey, that's 0. Okay. Your calculator should give you that, and you can always do that double check. And then force 3, we look at the picture. Force 3 is drawing down. And so you should already can see that there's going to be a 0x component, but if you want, you can use the 270 degrees and say, okay, force 3x is equal to this 500 newtons times cosine of 270, which shouldn't be too surprising that that's going to equal 0. And that force 3y is going to equal to 500 newtons times the sine of 270. And that should give us a negative 500. So we can take this information. We have now broken down all of these forces into their components. Now how we present this information is up to you. Now notice, even in this process of breaking down this triangle, there were the techniques of either just using the angle from the x-axis or just looking at the angle between whatever axis it is and breaking it into the x and y components. So you could, for instance, for force 2, you knew it was going in the x direction, so you could go ahead and say it was negative 250 in the x and 0 in the y. Or you could just put everything in terms of the x-axis, the positive x-axis, going counterclockwise from the positive x-axis in the angle form, and it should come out in your calculator the same way. But always do that double check. So let's take this further and show you how to do this with the net force. So one way you could do this is you could sum up all that's going on in the x and make a little table, and everything that's going on with the y. And so I'll put this as force 1, force 2, and force 3. Now as we saw in the last problem, the force 1 had an x and y component, and so we got 600 cosine 45 degrees and 600 sine of 45 degrees. And then force 2, we discovered that was all in the x direction, and it was negative 250 newtons. And there was nothing in the y direction, so I put a 0 there. The same thing for force 3. We have, except in this case it's going southward, so we get 0 in the x direction, but a negative 500 newtons in the y direction. Now when I do this, I then have this table with my list of things that are going on in the x and going in the y, and so I'm going to draw a line and say, hey, everything in this x column is going to add up to my net force in the x direction, and everything in my y column is going to add up to my force in the y direction. And some students jump ahead and say, hey, this is going to equal to the mass times the acceleration. Sorry, it's giving me issues. Mass times the acceleration in the x direction, and mass times the acceleration in the y direction. Now, the other technique that you could do is you could then take this and say, okay, I'm going to sum up all my forces in the x direction, and that's going to be my force 1 in the x direction plus my force 2 in my x direction plus my force 3 in my x direction. And sum up all the forces in the y direction, and that would be my force 1 in the y plus my force 2 in the y plus my force 3 in the y. Similar approach as this table, except I just took what I had figured out in the first part and just went ahead and started to create the summation of forces and summation of in the x and the summation of forces in the y. We're doing the same thing here. It's just whether you like the visual of a chart Or do you like more of the equation type look, where you sum up and say, okay, I got all the x components of all my forces, so I'm going to add them all up. And you can bypass this chart. But the chart is doing the same thing as this equation that I have here. And you could say, hey, my summation of my forces in the x is just going to be mass times acceleration in the x, and my summation of my forces in y is mass times acceleration in y. Either method will work. Now, the last method that you can do is the technique where this last method is where we can just create this in the I hat, J hat, K hat format. So for force 1, I could go ahead and I can not do the chart technique. I could not do the summation of the forces in the X, Y, and Z technique. I could just write this as a nice vector equation, right? The vector notation equation with the I hat, J hats, and K hats. And so my force 1 here is going to be 600 cosine 45 degrees times I hat, right? Because I have this I hat here. This is everything that's happening in the X direction, plus 600 sine of 45 degrees J hat. Now there is no K hat, so you can either write this as plus 0 K hat, or you could just ignore it. You don't always have to worry about K hat, but sometimes you do. And then we know that our force 2 is going to be equal to negative 250 I hat. And of course you need to make sure you keep your units in all these. So I'm going to put bracket newtons, and here I'm going to put my bracket newtons. And then the last one, force 3, and I need to probably put my arrows right here because this is a vector notation. Force 3 is going to be equal to 0 I hat minus 500 J hat. Now notice I didn't put J hat in force 2, but I could have. I could have also put K hat here. It just would be a 0, right? So I could have done a 0 J hat here. So you know, to fill in this equation more. And then in this technique, what you would do is you say, okay, my net force is going to be the summation of my force 1, force 2, and my force 3. And what you would do is you would group all your I hats together. So you get 600 cosine 45 minus 250 quantity I hat. And you would have, when you add all this together, and then you would have all your J hat components added together, and so then you would have 600 sine 45 degrees minus 500 quantity J hat, and of course for the 0, for the K hat, you would have just 0 K hat. And so then you would have your net force equation and do this calculation. And we know that the net force is going to also equal to mass times the acceleration. And so from here you could then figure out the acceleration vector by dividing that net force vector by mass. All of these approaches will lead you to the same direction for this problem. And so the question that you have to ask yourself is, do you like putting everything in vector notation and dealing with an equation, adding it up this way where you're putting all your I hat, J hat components together? Or do you like the table method? Or do you like to sum up all the X components, sum all the Y components, and they're in their own little groups, right? These are 3 different techniques that you will only know which way you like to solve problems until you try them. So please go and try and figure out which technique makes sense to you and which way will help you with solving these problems. I hope you have a good rest of the day, and I hope this helps. Thanks.